So, last time we had talked about electron configurations and orbital filling, and we had just touched on core electrons and valence electrons. Valence electrons are the electrons of the outermost energy level, and the core electrons are the inner electrons. They're all the other electrons. Valence electrons participate in chemistry. Core electrons do not. They just shield the valence electrons from the nucleus. One of the uses of this distinction is that it allows us to only focus on the electrons that matter and ignore the rest. So, when you look at lithium, lithium has 3 electrons. Its electron configuration is 1s2, 2s1. And you look at oxygen, its electron configuration is 1s2, 2s2, 2p4. Now, for lithium, its valence electrons are the 2s electrons, that's the outermost energy level. And the core electrons are the 1s electrons. For oxygen, valence electrons are these 6 electrons, 2s2, 2p4. And these are the core electrons. It's 2 1s electrons. In both cases, the core looks exactly like helium, 1s2. So we can abbreviate the electron configurations as lithium is a helium core and then a single 1s electron. And oxygen, likewise, is a helium core, but it has 2s electrons and 4p electrons. Now, for these smaller atoms, these lighter elements, this abbreviation doesn't make a heck of a lot of difference, but it does make a difference for the heavier elements. Okay? So let us look at iodine. Come over to the periodic table. Iodine is element 53. Okay, so it's going to have a total of 53 electrons. So, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. Now, over here, we have the valence electrons, and this is the core. Clear? It's the core. All right, and the core, going out to 4p6, looks exactly like krypton, with its 36 electrons. So the abbreviated electron configuration for iodine is krypton, 5s2, 4d10, 5p5. So it makes a pretty big difference when you're looking at a big atom. Okay? So that is very helpful. It's quite helpful. Now, you'll notice that every single time I've abbreviated, I've been talking about these noble gases. And so that is your shortcut for these electron configurations for heavier elements. The core is always going to look like the previous noble gas. Not the closest noble gas, the previous noble gas. Okay, so iodine, the previous noble gas was krypton. Okay. For chlorine, the previous noble gas would be neon. For vanadium, number 23 over here, the previous noble gas is, coming to the left, argon. Okay. So, whichever way you want to think of it, going down to the previous noble gas, or this might be another way you can do it. Okay, just go to the right, and then up. Okay, so selenium, you go right, and then up to argon. Bismuth, you go right, and then up to xenon. Okay? So long as it correctly gets you to the previous noble gas, I don't care how you get there. Okay? I never care how you get the right answer, so long as you always get the right answer, right? Well, except for cheating. Don't cheat. Cheating is bad. I kill you. All right. Now, another thing that you need to see is this guy right here, okay? The full D subshell. When you're over in the P block, when you're over here amongst the post-transition metals, the metalloids, and the nonmetals, okay, over here, we call it the P block. The D subshell is full over here in the P block. So it is, basically, what is wrong with this stupid pin? So the D electrons for iodine, sorry for the interruption, act as core electrons because it's completely full of electrons, and a full subshell like that has lots and lots of resonance. So all that resonance means that full D subshell does not react. Okay, so really, this is valence and this is valence, and the D subshell here for iodine over in the P block is an honorary core. Basically, we have to show it over here on the right because it is not part of the krypton abbreviation, but it doesn't participate in chemical reactions. So here we have our examples: oxygen, helium, 2s2, 2p4, copper is argon, 4s1, 3d10, or 4s2, 3d9. Copper is a semi-exception. And then we have lead, xenon, 6s2, 4f14. Don't forget the F subshells. 5d10, 6b2. Remember, when you're down here, level 6 and 7, you have the F subshells sort of squeezed in between S and P. Okay, so that's these two down here. Don't forget those when you're down at the bottom of the periodic table. You lose points. Okay. And for both of those, you have an honorary core. Okay, when you have those full subshells for F and D. For the S electrons, there can be no resonance, so the only way it could be core is if you have another energy level outside it. And for P, when you fill up the P electrons, you've reached the end of the row, and you're at a noble gas. So that's the only time it's going to be core as well. And speaking of the noble gases have no valence electrons. Okay? Noble gas are all core. Okay? Noble gas, all core. All right. So electron configurations are what we've been looking at, what we've been writing out. And the two different terms that I can ask for on a test is the full electron configuration, where you have to write out every single electron. And if I'm feeling particularly cruel or vindictive, or if I just don't like you, Richard, you know who you are, then I'll make you write out the full electron configuration. Okay? An abbreviated electron configuration, you take the core, you turn it into the previous noble gas, and only write the valence electrons. Quicker, easier to write. And that does it for our discussion of quantum mechanics and the structure of orbitals and electron configuration. So hopefully you'll be able to get from this the shapes, the names, and shapes of orbitals. Okay, so S, P, D, and F. But also you should get also their shapes. So sphere, peanuts, and this is the third dimension. This is going into and out of the screen. Then you have the clover leaf. That's terrible. The clover leaf. And finally F. No, that's a mean face. I want a scared face, crying. makes people cry, so we don't have to draw F. But you do have to draw S, P, and D. Also, know about full and abbreviated electron configurations. Know that S is 1 orbital P, there are 3 orbitals, there are 5 D and 7 F. You need to know about orbital filling, so okay, so on. So that it goes 1S, 2S, 2B, 3S, 3B, 4S, 3D, 4B, and so on. And you need to be able to, you also need to remember Hund's rule. And I think that covers most of the material from this chapter. What you don't have to do is any sort of math for this chapter. Oh, definitely do not forget resonance, because that will show up again in later chapters, later sections.